아, 네. 그래서 이제 오늘 이제 열 번째 수업이고 이제 오늘 아무래도 추석 주간이라서 수업 수요일 날 목요일 수업이 제가 이제 미리 같이 올려서 화요일 날부터 같이 시청을 할 수 있게 하겠습니다. 그래서 오늘은 이제 추석이고 그다음에 우리가 추석 주간이라서 진도를 나아간다기보다는 우리가 이제 우리가 배웠던 라이트 스캐터링, 뭐 삼투압, 오스모틱 프레셔, 그다음에 인트린식 비스커시티 이 세 가지들이 이제 사실은 뭐 고분자의 체인 사이즈를 알아내는 방법이라고 제가 지금 얘기를 했었었고, 뭐 모레큘러 웨이스 알아내는 방법이고, 실제로는 사실 지금도 많이 사용하긴 합니다만 그 요새는 이제 GPC 그 젤 퍼미에이션 크로마토그래피라는 게 사실 그 각각 그 오스모틱 프레셔가 측정을 할 수 있었던 넘버 에버리지 모레큘러 웨이트, 그다음에 라이트 스캐터링이 측정할 수 있었던 그런 웨이트 에버리지 모레큘러 웨이트가 그다음에 인트린식 비스커시티까지가 사실은 요새는 GPC 자체적으로 모두 분석이 가능합니다. 그래서 GPC에 대해서 우리가 수업을 좀 더 자세하게 나갈 거고, 사실 그 GPC 자체가 그 세 개를 다 가능하게 한다는 게 그 새로운 기술이 있는 게 아니고 사실 라이트 스캐터링과 그러한 몇 가지 요소들이 다 GPC 안에 탑재가 되어 있다고 보면 될 것 같아요. 그래서 이제 오늘은 GPC에 대해서 수업을 진짜로 나간다기보다는 GPC의 개발된 그런 역사적 배경과 여러 가지 그런 그냥 오버뷰 형태의 이야기를 하고, 그 다음에 이제 GPC 말번이라는 GPC 회사가 소개해주는 이런 GPC 인트로 영상을 보면서 오늘 수업을 마치도록 하겠고, 그 다음에 다음 시간에는 이 GPC를 우리가 정말 다시 진도를 나가면서 제가 다 차근차근 다시 한번 이 영상에 대해서 설명이 한번 더 들어갈 거라고 생각을 하면 될 것 같습니다. 그렇고 그래서 GPC는 지금 이 사진에서 보여지는 것처럼 어떻게 보면은 굉장히 생각보다는 오래되진 않았습니다. 그래서 이 보면은 제일 첫 번째 GPC 세미나 때 사진인데, 이거 보면은 1965년이라고 되어 있죠. 그래서 우리가 이제 다우 케미칼이라고 하는 미국의 되게 거대한 이제 뭐 이런 화학 회사가 있는데, 거기 이제 이분이시고, 그 다음에 이 월터 코퍼레이션의 짐 월터라는 사람은 사실 이런저런 그런 디텍터 사업을 하시는, 조그마한 사업을 하시는 분이었는데, 이제 GPC를 이제 개발하는데 그 디텍터를 지원을 해준 초기 사람 중에 하나입니다. 그래서 이런 식으로 GPC에 대해서 1965년 정도에 이제 새로 이런 개념이 나왔고 이런 제품이 생산되기 시작했습니다. 그래서 1965년이고, 그래서 이제 제일 처음에 나왔던 GPC 모델이 지금 여기와 같이 보여지는데, 실제 사이즈가 거의 냉장고 사이즈만 했다고 해요. 1965년도에 나왔을 때는. 그래서 이제 사람이 거의 서 있으면은 뭐 사람이 거의 이 정도로 올 수 있는 사이즈로 거대한 사이즈였다고 합니다. 근데 지금은 이 GPC가 아마 아시는 분은 아실 텐데, 대략적으로 사람이 옆에 쓴다면 허리까지 아마 사람이 이렇게 옆에 쓴다면은 뭐 이렇게 허리까지 올 겁니다. 그래서 허리 밑으로 오는 정도의 사이즈 정도라고, 아주 작은 건 아니지만 그래도 냉장고 사이즈로 치면 굉장히 많이 작아졌다라는 것으로 우리가 이해를 하면 될 것 같아요. 그래서 이제 보면은 제일 첫 번째 나왔던 GPC가 그때 당시 1965년도 당시에 12,500불이라고 하는데, 12,500불이라고 하면은 현재 돈의 가치로 2016년 기준인데 1억 정도 하는 겁니다. 1억에서 1억 5천 사이 정도의 돈이고, 현재 GPC는 이렇게 대략적으로 5천에서 1억 사이, 사실 크게 금액에 대한 차이는 없고, 대신에 이제 가격은 좀 비슷하지만 이제 여러 가지 이제 기능들이 좀 추가가 되었다라고 우리가 생각을 하면 될 것 같습니다. 그래서 일단은 그 타임라인을 봤을 때, 우리가 이제 시간을 만약에 보고 있다, 시간을 보고 있을 때, 시간 말고 연도를 보고 있을 때, 1965년에 이제 GPC가 출현을 하게 됩니다. GPC의 탄생. 그래서 그 이후로는 이제 GPC의 세대가 온 거죠. 이 고분자의 길이를 분석하는. 근데 이 전에 1965년도 전에는 우리가 알고 있던 그 마코잉크 이퀘이션을 사용한다든지, 혹은 오스모틱 프레셔, 혹은 라이트 스캐터링 등을 이용해서 MN, MW를 각각 측정을 하는 방식으로 이루어졌습니다. 그에 반면에 지금 GPC라고 하는 젤 퍼미에이션 크로마토그래피는 MN, MW, 뭐 PDI 등등을 한 번에 동시에 측정할 수 있다는 굉장한 장점을 가지고 있습니다. 그렇고 대략적으로 그 다음에 우리가 1950년도 정도에 이제 우리가 음이온 중합이라는 게 어느 정도 학계에 발표가 되고, 이제 고분자 합성에 있어서 어떻게 보면은 제일 그런 전성기가 온 거죠. 이제 원하는 고분자의 길이를 원하는 그 네로우한 디스트리뷰션으로 만들 수 있는 그 합성법이 개발되면서 실제로 이런 분자량을 측정하는 데 대한 니즈가 엄청 많았다가 그 니즈에 부합하게 이제 GPC가 이제 개발이 되었고, GPC는 지금 얘기하는 것처럼 이런 것들, 전에는 오스모틱 프레셔라든지 라이트 스캐터링이라든지 이런 것들이 하나씩 측정할 수 있었던 것들을 GPC는 동시에 측정을 가능하게 해줍니다. 근데 이제 그 반면에 얘네들은 그래도 어떻게 보면 앱솔루트 캐릭터라이제이션 메소드라고 해서 무슨 고분자를 넣어도 그 고분자의 정확한 그 길이, 모레큘러 웨이트가 넘버 에버리지 모레큘러 웨이트를 그 그 평균값을 구할 수 있는데, 반면에 이 GPC는 상대적인 방법입니다. 절대적인 방법이 아니고 상대적인 방법이고, 뭔가 기준에 대해서 걔에 비해서 얼마나 높냐, 얼마나 낮냐 이런 식으로 나오게 되는, 어떻게 보면 단점이라면 단점인데, 그런 장점이라고 하면은 이런 것들을 한 번에 측정할 수 있다는 거, 한 번에 측정이 가능하다는 거. 하지만 단점은 얘네들은 그래도 절대 방법은 아니다, 상대적인 방법이다라고 우리가 알아두면 될 것 같습니다. 그러다가 이제 1967년에 유니버설 GPC라는 이 유니버설 캘리브레이션이 되어 있는 이 GPC의 개념이 도입이 되면서, 이때부터 사이즈 익스클루전 크로마토그래피라고도, 혹은 SEC라고도 이제 불리기 시작하면서 그 전에 GPC는 로그 모레큘러 웨이트과 일루전 볼륨 사이에 플랫을 했었으면은 SEC부터는 우리가 좀 더 그 인트린식 비스커시티 곱하기 모레큘러 웨이트 로그를 일루전 볼륨과 관계 짓는 형태로 되어 있는데, 이제 수업을 진행하면서 제가 더 이야기를 할 건데, 이런 식이 되면서 실제로 좀 더 그 상대적인 방법이지만 꽤나 다양한 고분자에서도 정확한 분자량을 측정할 수 있음을 나타났습니다. 네, 그래서 그렇고, 그래서 이런저런 이 1950년대, 40년, 1900 그 초중반기에 이제 고분자 그의 그런 그때 당시에 이제 세계 뭐 2차 대전, 뭐 1차 대전 이런 것들을 이제 전쟁을 하면서 세계 2차 대전 때 그런 고무에 대한 수요와 이런 그런 것들이 이제 개발이 되면서 이제 그 고분자 산업이 부흥을 하다가 실제로 1950년 정도가 되었을 때 음이온 중합이 가능해졌고, 그부터 이제 점점 그 고분자의 길이를 측정하는 방법들이 더더욱 발전하기 시작했었습니다. 그래서 그렇고, 그래서 아까 얘기한 것처럼 오늘 수업 끝내기 전에 그 말번이라는 회사의 그 GPC에 대한 그 개요 영상을 보면서 오늘 수업은 마치도록 하겠습니다. 그래서 추석 잘 보내시고 바이러스 조심하시고, 그다음에 다음 주 돌아오는 주에 이제 GPC에 대해서 수업을 진행하도록 하겠습니다. 네, 수고 많았습니다.
An introduction to GPC in 30 minutes. This presentation will include an overview of GPC, what it is and some common applications. Then we'll explore chromatography, the analytical technique that provides the foundation for GPC. Next, we'll look at the detectors, which are the devices that allow the users to see and observe the sample as it is analyzed. After that, we'll examine how that raw data is processed into molecular weight and many other types of characterization data that make GPC such a popular analytical tool, and then we'll wrap things up. First, let's start with an overview of GPC. GPC stands for gel permeation chromatography. GPC is a type of size exclusion chromatography, often abbreviated SEC. While GPC refers to a specific type of SEC, the two are very similar and are often used interchangeably, as GPC is the most common type of SEC. GPC-SEC describes an analytical technique that is used to characterize macromolecules, providing data such as molecular weight, intrinsic viscosity, and hydrodynamic radius. These traits often affect the physical properties of the material and/or the behavior of the particular compound, and are of great interest to researchers, production plants, and manufacturers. Examples of materials frequently analyzed by GPC are natural polymers, such as dextran, chitosan, and cellulose, synthetic polymers, including polystyrene, polyethylene terephthalate, and nylon, and proteins, such as oligopeptides, antibodies, and membrane proteins. So what is chromatography? The C in both GPC and SEC stands for chromatography, which refers to a set of laboratory techniques involving the separation of mixtures. Chromatography involves passing a mixture carried by a mobile phase through a stationary phase, which separates the constituents of the mixture based on differential partitioning between the mobile and stationary phases. In the animation at the bottom, a mobile phase is shown passing through the stationary phase, which is usually located in a column. If we take a sample mixture and load it onto the column, the mobile phase will begin to move the sample mixture components through the stationary phase. The sample mixture components will travel through the stationary phase at different rates based on molecular differences between the individual components. This means the individual components exit the stationary phase at different times, providing a separation of the mixture. So, what's unique about GPC and SEC? Size exclusion chromatography describes a class of chromatography that, as the name suggests, separates analytes based on their size. SEC is a solution-based technique, which means it uses a liquid as the mobile phase to carry the analytes through the chromatography column. As the mixture of analytes travels through the stationary phase of the column, the sample components are separated according to molecular size, with larger molecules eluting first. It is important to remember that separation is based on hydrodynamic size, not molecular weight. So now we know that GPC separates molecules based on size, but how does it work? Well, if we take a closer look at the stationary phase, we can see that the column gel is made of particles that contain pores. The presence of these pores is the key to making GPC work. The separation process operates based on the diffusion or permeation of the analyte molecules in and out of the pores on the gel particles of the stationary phase. As we can see in the animation, the largest molecules, represented by the triangle, spend the least amount of time inside the porous gel particles. The intermediate-sized squares can diffuse partially into the pores before moving to the next, while the smallest circles can easily diffuse in and out of the pores and penetrate all the way in and thus require the most time to elute. Think of it like a bag of potato chips. When you open a brand new bag, the large chips are located at the top because they can't fit through the spaces that fall to the bottom. However, by the time you get to the end of the bag, you're left with all the broken chips and crumbs that can fit through the spaces and have gathered at the bottom. These crumbs are the same as the smallest components of your sample, like the circles shown here, which spend the most time within the spaces and pores and elute last from the column. On the right is the elution profile for a column set, showing the molecular weight range of the molecules this particular column set can resolve. The resolution obtained during the analysis of a sample is dependent upon the specific GPC column set. Which brings us to GPC columns. The chromatography process we've discussed occurs inside of the GPC column set. Ultimately, good results come from good chromatography, for which to obtain you need the appropriate GPC columns. Luckily, there are many types of GPC columns available to fit your sample needs. Some common factors to take into consideration when choosing a GPC column set include mobile phase compatibility, which is generally the primary concern, molecular size and molecular weight range, compatibility with your sample or functional groups present on your sample, or alternately, what is the chemical identity of the column gel, and how many columns of which type do you want to use. Multiple columns of the same type to increase resolution, or columns in consecutive molecular weight ranges in order to expand the resolution range. To highlight the variety of solvents used as mobile phases, here are some of the types of GPC columns that Malvern offers. T columns for THF or other organic mobile phases such as DMF, chloroform, and hexafluoroisopropanol. A columns for the analysis of general aqueous polymers in a variety of aqueous mobile phases. P columns for the analysis of proteins in aqueous mobile phases. High temperature GPC columns for analysis at elevated temperatures, and specialty columns such as I columns which contain an inert stationary phase that prevents sample adhesion, and cationic columns which have a cationic stationary phase in order to repel cationic samples. Shown here is a schematic for a complete GPC system. The columns and chromatography process we described are located in the center of the image. The system components in line prior to the columns are necessary parts that keep the system running, such as a mobile phase reservoir, a vacuum degasser to remove air from the mobile phase, the pump to maintain mobile phase flow, and the injection loop with optional autosampler that introduces a sample mixture onto the column set. So, now that we've injected our sample and used chromatography to separate our mixture, we need a way to observe the individual components present. Which leads us to the detectors, how we see our samples. After the GPC column set does all of the hard work involved in the separation process, we need some way to observe the effects of the chromatography. This is where the detectors come in. The detectors are individual devices that respond to different characteristics of a sample. The more detectors we use, the more information we can learn about a sample. The most common detectors used in GPC are a refractive index detector, a UV-Vis or photodiode array detector, a light scattering detector, and a viscometer detector. Various combinations of these can be used depending on the specific data desired. The refractive index detector responds to sample concentration. The UV-Vis or photodiode array detector responds to sample concentration and light absorption. The light scattering detector responds to the sample's molecular weight, and the viscometer detector responds to the intrinsic viscosity of the sample in solution, which is influenced by the sample's molecular density. Next, we'll take a closer look at each detector individually. The principle behind the refractive index detector is that light travels differently through different mediums, which is a phenomenon we see all the time in everyday situations, such as a straw in a glass of water. The light we see reflected off of the top of the straw travels in a straight line to the eye when it's uninterrupted. However, when the light travels through water and in air on its way to your eye, the light is bent or refracted at the interface of the two mediums. This is the exact same way a refractive index detector operates. A refractive index detector works by using a light source to project a beam of light through a flow cell that has two sides to it. One side contains just solvent, and the other side has solvent and sample. The light will refract at the interface and is reflected by a mirror back to a set of photodiodes. These diodes are at different voltages. One is positive and the other is negative. Depending on whether the sample refracts the light more or less than the solvent, the light will move more onto the positive or negative diode, giving either a positive or negative peak. The amplitude of the signal corresponds to the concentration of the sample, as well as the material's DNDC value. The DNDC value, or refractive index increment, shown in the equation on the left, is a term that correlates the refractive index response to sample concentration, and is a unique value for a given sample and mobile phase pairing. Instead of using refracted light, the UV-Vis detector works based on the principle of light absorption. Many chemicals absorb certain wavelengths of light, leaving the other wavelengths of light to be reflected back to our eye. That's how we end up with chemicals of different colors. The colors we see are from wavelengths of light reflected back that exist in the visible region. There are also many wavelengths of light that are absorbed or reflected by compounds that we are unable to see. These are the ultraviolet, or UV wavelengths. UV-Vis detectors are commonly used particularly for protein analysis. A limiting factor for UV-Vis detectors is that the material being analyzed must have a chromophore in order to produce a signal. UV-Vis detectors work according to Beer's law, which is why they are responsive to sample concentration and can be used as a concentration detector in a GPC setup. Most UV-Vis detectors are single-channel detectors, which measure one wavelength at a time. A photodiode array, or PDA detector, measures all wavelengths simultaneously, so the user can choose which wavelength to view after data has been acquired. It is important to note that when working with UV-Vis detectors, the DADC term relates the signal response to sample concentration, just as the DNDC value does for refractive index detectors. Light scattering detectors are based on the fact that when light from an incident beam hits a molecule, the light is scattered. And most importantly, the intensity of this scattered light is directly related to the molecular weight of the molecule. While all measurements from light scattering detectors operate by observing the intensity of the scattered light, there are different ways those detectors can be arranged. This leads to a few different light scattering detector options. Shown on the left is a scheme of Malvern's dual-angle light scattering detector, in which a right-angle detector and a low-angle detector are combined to provide a direct measurement of molecular weight for samples of all sizes and molecular weights. On the right is a general scheme of Malvern's multi-angle light scattering detector. Over the next few slides, we'll look at each type of light scattering detector in more detail. It is important to remember that the light scattering detector response is most strongly affected by the molecule's molecular weight. The right-angle light scattering detector, as the name suggests, positions the detector at a 90-degree angle from the incident beam. This detector works best for relatively small molecules, roughly smaller than 15 nanometers, because they scatter light isotropically, or the same in all directions. Since the intensity of the light is the same in all directions, the angle of observation becomes irrelevant. This is visually depicted by the partial Zim plot on the bottom right of the screen, in which the molecular weight observed is the same regardless of angle. This consistency means that the molecular weight of a molecule can be determined directly by observing the intensity of the scattered light at any angle. Therefore, the right-angle light scattering detector is optimal in this case because it provides the least amount of baseline noise as a result of its orthogonal placement relative to the incident light beam, thus providing the best signal-to-noise ratio. The low-angle light scattering detector positions the detector at a 7-degree angle from the incident beam. This location is important because when molecules do not scatter light isotropically, meaning that there is an angular dependence on the intensity of scattered light, then the intensity of scattered light observed at the zero angle is the most accurate measurement of molecular weight. Of course, having a detector at the zero angle is not practical, as the detector would observe the full blast of the incident beam. By placing a detector 7 degrees off of the incident beam, the low-angle light scattering detector can make the most accurate, single direct measurement of molecular weight. While this low-angle light scattering detector offers the best method of directly measuring the molecular weight of macromolecules, it is especially important for materials larger than 15 nanometers. This is because those relatively large molecules do not scatter light the same in all directions, due to constructive and destructive interference. Since the intensity of scattered light observed depends on the angle of observation, as shown in the partial Zim plot on the bottom right of the screen, it is critical to observe the scattered light as close to the zero angle as possible. Another method of determining molecular weight from light scattering measurements involves the use of a multi-angle light scattering detector. Previously, we discussed how not all molecules are isotropic scatterers, and therefore the intensity of scattered light is not always the same at every observation angle. The low-angle light scattering detector obtains accurate molecular weight by observing the light scattered as closely to the zero angle as possible. An alternate method is to observe the light scattered at numerous angles, hence the name multi-angle light scattering, and then use the partial Zim plot to extrapolate back to the zero angle to determine molecular weight. The principle behind the viscometer detector is that a solution containing dissolved macromolecules will be more viscous than the solvent by itself. Comparisons of the two lead to a variety of viscosity values, including intrinsic viscosity. The 4-capillary viscometer allows the intrinsic viscosity of a sample solution to be measured directly. This is done by observing the differential pressure, delta P or dP, and the inlet pressure, or IP. Those two pressure measurements allow for the specific viscosity of the sample solution to be obtained. Intrinsic viscosity is the specific viscosity of a sample solution at infinite dilution, and is usually determined by obtaining the specific viscosity at varying concentrations and extrapolating back to zero concentration. However, since the concentration of the sample solution in GPC is very low, it is close enough to zero concentration that the specific viscosity determined is essentially the intrinsic viscosity of the sample. Here is an animation of what happens in the viscometer as a sample passes through. Initially, there's only mobile phase in all capillaries, which provides a baseline reading and a differential pressure of 0. When the sample is introduced, it is split between the positive and negative sides of the viscometer bridge. The negative side of the viscometer bridge, shown here as the top half, contains a delay reservoir, which holds the sample and allows the solution pressure of the sample in the positive side of the viscometer to be compared to that of the solvent on the negative side of the viscometer. This creates a positive peak in the dP signal, which corresponds to the sample. The sample elutes, and the viscometer signal returns to baseline until the sample that has been held in the delay reservoir finally begins to elute. Because this increased pressure is now on the negative side of the viscometer, a negative peak begins to form in the dP signal. Once the sample elutes from the delay reservoir, the viscometer bridge now contains only mobile phase, and the dP signal of the viscometer returns to baseline. This slide provides the equations that dictate the response of each detector. All detectors are affected by the amount of analyte present, which is represented by the concentration and injection volume terms in each equation. The K term in each equation are the individual detector constants, and as such, are not sample dependent. This leaves the underlying term in each equation, which is the parameter that most strongly affects each detector's response. The concentration detectors, the refractive index and UV-Vis or photodiode array detectors, are most sensitive to the dNdC and dAdC values, respectively. These terms correlate the sample concentration to the detector response. If a sample has a high dNdC or dAdC value, then it is likely that it will provide a strong detector response. For the light scattering detector, there are two key terms, the dNdC value, which appears as a squared term in the Zim equation, and the sample's molecular weight. While both terms certainly have an effect on the resulting signal, as long as there's an adequate dNdC to observe the sample with the refractive index detector, then the light scattering detector signal will respond most strongly to the sample's molecular weight. The viscometer detector responds most strongly to the intrinsic viscosity of the sample solution. If a particular sample does not produce a strong viscometer response, that doesn't necessarily mean there's anything wrong with the detector. Small, dense materials do not produce a high intrinsic viscosity and would therefore have a much weaker detector signal than a sample of low molecular weight that is well solvated and expanded. So now let's take a look at the analysis methods, or how data is calculated. So now that we have all of that wonderful raw data from the detectors, how do we turn that into meaningful information that helps us characterize our sample? There are three main types of data analysis, and each provides a different level of molecular characterization. The first analysis method we'll discuss is conventional calibration, which involves the use of a concentration detector to build a calibration curve with a series of standards. The sample is then measured against this calibration curve to provide relative molecular weight values. The second analysis method is universal calibration, which uses a concentration detector and a viscometer detector. The addition of the viscometer detector accounts for the difference in molecular size and shape between the standards in the sample. Universal calibration provides intrinsic viscosity and true or accurate molecular weight values. The third analysis method is advanced detection, also known as triple or tetra detection, depending on which detectors are employed. Advanced detection uses a light scattering detector and a viscometer in conjunction with at least one concentration detector in order to provide intrinsic viscosity and absolute molecular weight values. Conventional calibration relies on a single concentration detector, either a refractive index or UV-Vis or photodiode array detector. Because of this single detector setup, conventional calibration is the most economical GPC analysis method. In order to perform a conventional calibration, a series of well-characterized standards must be run. These standards should cover a wide size and molecular weight range so that the entire breadth of your column resolution range is mapped. Once the molecular weights of the standards have been entered and assigned to the corresponding retention volume, the software will determine the best fit line, which will serve as the calibration curve. When a sample is analyzed, the molecular weights are extrapolated from the calibration curve based on the retention volume of each point. It is important to note that conventional calibration is based entirely on retention volume. Since the molecular weight values obtained through conventional calibration are extrapolated from the calibration curve, the values calculated are relative to the standards used. This is why you'll often see data presented like sample A had a molecular weight of 10,000 Daltons relative to polystyrene standards. Since conventional calibration data is based on the retention volume of a sample, every GPC system will have a unique calibration curve, even when using the same standards. Parameters such as columns, mobile phase, flow rate, and temperature will affect the retention volume of the standards and thus the resulting calibration curve. Likewise, every polymer type has its own calibration line. Remember that separation, and thus elution order, is based on hydrodynamic size. If polymer A and polymer B have different structures, then a 50,000 Dalton sample of polymer A will have a different size and thus elution volume than a 50,000 Dalton sample of polymer B, even though they have the same molecular weight. Therefore, a calibration curve from standards of polymer A will give different results than a calibration curve built from standards of polymer B. Additionally, two samples that have the same molecular size but different molecular weights will appear identical using conventional calibration. Along those same lines, the accuracy of data from conventional calibrations depends on how similar the molecular structure of the sample is to the standards. The closer the molecular structure of the standards and sample are, the more accurate the data will be. And last, the data that's acquired from conventional calibration is limited to molecular weight moments, as shown to the left. Since conventional calibration uses only a single concentration detector, no viscosity, size, or structural information is available. Next, universal calibration uses the combination of a single concentration detector, either a refractive index or a UV-Vis photodiode array detector, with the addition of a viscometer detector. The addition of the viscometer detector is important because, back in 1967, Benoit used a relationship between hydrodynamic volume, molecular weight, and intrinsic viscosity to show that the calibration curve for polymers of different types can merge into a single calibration curve. Remember, GPC separates based on molecular size, or hydrodynamic volume. Therefore, if we think of elution volume as essentially being hydrodynamic volume, we can plot molecular weight times intrinsic viscosity against hydrodynamic volume. This means that all polymers, regardless of structure and shape, will fall along the same calibration curve. In addition to providing intrinsic viscosity and the related size information, a universal calibration curve eliminates the need to have standards that are the same as your sample in order to calculate accurate molecular weight data. Since the molecular weight values obtained through universal calibration account for molecular structure and shape, the values calculated are described as true or accurate, regardless of the standards used. Even though the identity of the standards doesn't matter, a calibration curve is still required, and therefore every GPC system will have a unique calibration curve. Parameters such as columns, mobile phase, flow rate, and temperature will still affect the resulting calibration curve. Every polymer falls on the same universal calibration curve, which means that the accuracy of the data is improved from conventional calibration results. And last, the data available includes molecular weight moments, just like conventional calibration, but now has the added benefit of providing intrinsic viscosity, hydrodynamic radius, and Markowink parameters. Advanced detection, also known as triple or tetra detection, introduces a light scattering detector to the array. This combination of detectors provides complete characterization of your GPC samples. If we revisit this list of equations, you can see that each detector responds to a unique combination of factors, but more importantly, each detector tells us about one different aspect of the sample. So the refractive index detector provides the sample concentration information. The UV-Vis or photodiode array detector allows sample concentration and absorption information to be obtained. The light scattering detector offers a direct measurement of the sample's molecular weight, independent of a column calibration curve, and the viscometer detector measures the sample's viscosity in solution, which is then used to calculate the intrinsic viscosity and hydrodynamic radius of the sample. And as you can see, all the detectors operate simultaneously, providing a wealth of data from a single injection. So advanced detection provides absolute molecular weight values, meaning no calibration curve is necessary. The molecular weight is calculated independently from the light scattering detector. A single narrow standard is used to determine instrument constants and detector offsets. The accuracy of the data is independent on the identity of the standard. And each detector tells a different piece of the story. Sample concentration from the RI and UV-Vis or photodiode array detectors, sample viscosity and size information from the viscometer detector, and molecular weight from the light scattering detector. And with advanced detection, there is an incredible amount of data available from a single injection. Molecular weight moments, intrinsic viscosity, hydrodynamic radius, radius of gyration, structural information, concentration, recovery, and potentially absorption profile and compositional analysis. And now to wrap up with some conclusions. So GPC is the most common analytical tool for characterizing natural and synthetic macromolecules, from materials as diverse as plastics and rubbers to proteins and peptides. GPC is a technique that separates the analyte molecules based on molecular size. It is part of a larger class of techniques called size exclusion chromatography. A variety of detector configurations can be used, usually employing some combination of refractive index, UV-Vis or photodiode array, light scattering, and viscometer detectors. In conventional calibration, universal calibration, and advanced detection are the three prominent analysis methods in order of increasing sophistication used to obtain different levels of molecular characterization.
Thank you for listening. For more information, please visit www